Okay, so hello everyone. So today I'm going to talk about the research direction that my group is actually following. It's not like that I follow all the time. It's also determined by my group also. They are the ones who are spearheading this whole effort of how do we actually design or tailor today's system software for both today's need as well as tomorrow's need. And one of the motivations that actually comes from is, okay, it works now, is if you look at the amount of data that we are generating from the IoT devices, from machine learning workloads, from data centers everywhere, it is growing by almost twofold every year. So there was a report which I actually used during my, when I was actually applying on the job market, that it was growing by almost 61% every year, and now it is growing by almost 30% on an year-by-year basis. So it is projected to grow by up to 175 zettabytes of data. Now, to put it in the context of people who can understand, or also for my parents and my family members, so when you think about 1 zettabyte of data, it is actually watching a regular HD size video for almost, I guess, around 63 million years. That's what 1 zettabyte translates to. But here we are talking about 175 zettabytes of data. Now, this data needs to be computed and processed and stored at some places. And if you look at this kind of data, what is happening is that various applications have been designed around this to exploit it. And you can think from the case of having your e-commerce workloads to social network to search engines, all of them are actually processing and using this data. Not only that, if you think about the applications, they have also changed or evolved over period, the same kind of applications. So there have been a lot of works that have come out and have talked about how the workloads have evolved in Twitter, which has become now X, or Meta, or which was Facebook earlier, that over the past 2 decades or a decade, their workloads have been changing a lot for the same kind of applications. Now, if you think about these applications, they are actually running inside data centers. And these data centers can have hundreds of thousands of machines consuming tens of megawatts of energy. Well, this is the estimate right now, but new data centers might have 1 gigawatt of energy that they would be using for just processing. And if you think about or take a look at one of the machines that is running inside this data center, it is also evolving. It is also very heterogeneous in nature. So for instance, there are like different types of CPUs which their capabilities have been increasing day in and day out. So you can think about the increasing number of core count or the CPU count is mostly used for computation purpose. For doing general purpose applications, it's like adding another lane to a highway to minimize congestion, which rarely works. And on the other side, we have also got these beautiful or expensive devices such as GPUs that are also used for processing purposes as well. And to a certain extent, there was this news that the B200 GPU that they have announced can actually do up to 20 petaflops of compute if need be. Now, this petaflop of compute is like 7.8 billion people performing a mathematical computation every second for the next 41,000 years. And here we are talking about 20 petaflops. This is not the only case. Now, if you take a case of storage devices or other media, that is also changing a lot. We have got various types of devices ranging from smart SSDs for storing data to smart NICs for actually communication purposes. And this keeps on changing again and again. This keeps on evolving again and again. Now, if we think about it, who is going to handle it? So, for instance, we have got these applications that wants to run on this hardware. And this is where system software comes into the picture. Now you can draw this system software analogy to a conductor that actually directs musicians in an orchestra. The conductor or the OS or the system software is responsible for managing different musicians, such as allocating tasks, which can be about directing a solo, allocating memory, for efficiency, which could be like putting people all in sync. Or you can also think about input and output, like signaling the sections of people to perform in cohort so that it can be done correctly. Now, if you don't have the conductor, what is going to happen is that the musicians would play out of sync or even clash, creating chaos instead of cohesive performance. And this is exactly the job of system software, or in particular, operating systems that are responsible for managing or act as a broker between heterogeneous hardware and the applications that are actually running. Now, in the past 2 decades, what has happened is that the whole OS design has been sort of going through the data-driven computing paradigm, where a lot of applications are creating or stressing out various components of the operating system, be it networking, be it storage, etc. And this actually creates a lot of performance issues. So just to give you a very concrete example here, so just to understand from this graph is that there is an application that is running, and the actual performance is what you get for the application. Meanwhile, the ideal case should have been a linear scalability increase, but it is far from reality when the developers are actually designing it. And the reason we actually see this kind of issue is because of the inefficient hardware utilization, as well as today's system software. If you think about this, they are not ready for tomorrow's need or even today's needs. Now, if we translate it at the level of data centers that are running like hundreds of thousands of servers, we are not only wasting the resources, we are also underutilizing them. And if we take a step back and try to understand why this is happening, what we will find is that the current software stack or the system software design that we have today, it is struggling to keep up with the changing requirements of hardware as well as the application requirements or application's behavior. The reason being is that most of the application design follows or is tightly coupled with the old requirements of when these applications came into the picture. They cannot keep up with the basic requirements of what it is today. And if you think about the analogy, you can actually think like this is that today's applications, they are like a Swiss Army knife, or today's system software are like a Swiss Army knife. For all the set of applications you want to run, they are not going to provide you good performance. I mean, not best performance, but good enough to survive. So they are only going to support general purpose cases as well. This is very similar to having a chat GPT which can answer some set of good questions, but not insightful answers if you need them. And this is exactly the same state of affairs we have for system software, where programs are running on machines that are general purpose. Although there is no harm in having a general purpose or like performance with respect to that. But when we think about efficiency, when we think about application requirement, we are not able to keep up with that. So the question that my group has been asking is, can we actually design system softwares or operating systems that can actually withstand the test of time? Well, it's a very provocative way of saying it, but the more important aspect here is that can they actually adopt or adapt with hardware changes or application requirement? And in particular, we have been focusing on 3 various aspects. The first one is about efficiency, where we are looking at how do we actually improve the efficiency of existing system software stack by coming up with different set of abstractions or redesigning various approaches. The second aspect that we are also exploring is how do we exploit the underlying heterogeneity that is becoming common today? Or the other way to look at it is that how do we actually hide it from the applications and still provide them the best performance possible? While doing all these things, what we have to keep in mind is that system software stack that is running is a sort of a broker that needs to work correctly and safe and efficiently. So how do we ensure its safety and correctness? this is a sort of the focus that we take forward. Now, if we dig deeper, what we find is that the current software stack today has been designed for generality. And if we want to tune or adapt these system software, what we would like to do is that they could actually adapt to the requirements of these applications. So there is a sort of a semantic gap that exists between applications and the system software. And this can be bridged through specialization that can actually allow them to tune them for the for the requirement of the application. Now, when we're talking about different type of applications that are running, what we have to keep in mind is that not all applications want this generalization. There are very few class of applications that want this kind of generalization. So how do we interplay, how do we balance this out? That becomes a very critical question. It's very similar to that you have ChatGPT and a professor, this is a professor, who is going to grant PhD students their degree, not the ChatGPT. Or you can think about a surgeon who is going to use scalpel for performing surgery. It's not the Swiss Army knife that is going to help the surgeon out. So based on that, let's take a look at a couple of works that my group has done on the lines of improving efficiency and heterogeneity. So we'll first start with the efficiency aspect. So the first work is the fast, flexible, and practical OS extensions. So OS extensions can be thought of as these are actually plugins or add-ons that safely extend the capability of the operating system. Well, you can think of OS extensions as like additional attachment that you can connect to the main unit to perform or extend its capability. Here you can think about a very simple example is the food processor, which is performing very basic operations like chopping, blending, or mixing. Well, you can extend its functionality by including a juicer or maybe, I guess, a pasta maker. So this is what is also true with respect to OS extensions that are responsible for extending the capability of the operating system. And as well as also you can understand or try to have safety aspect coming into the picture. Now, safety is something which is very critical. What I mean by safety here is that it should not compromise the integrity of the underlying core OS when it is actually running. If you do that, if the safety is compromised, that's when we have these CrowdStrike kind of events which actually brought down around 8.5 million machines all over the world, costing billions of dollars to a lot of companies all over the world. The other aspect that is very important with respect to extensibility is also looking at performance, flexibility, as well as looking at practicality. When we are thinking about extensibility, we want to maintain same set of performance that we had earlier or further improve it. The flexibility is more about you are not tied to a particular kind of an application to do the operations or to the framework to do the set of operations. And practicality is always about that it could be used by other vendors, other application developers, etc. So what we found is that if you think about today's extensibility or extension frameworks that are available for extending the capability of the underlying operating systems or the software stack, they actually miss the mark in the sense that they are either flexible or performant, but they do not provide both things at the same time. And when we think about performance, the performance is actually achieved through doing static verification or static analysis, which does not provide this notion of flexibility. Meanwhile, flexibility comes, you can get flexibility if you want by performing runtime checks, but it has its own performance overhead. So I actually thought about how do we actually explain this in a very simple words, thinking about static analysis and runtime checks. So you can think about static analysis as, suppose if you got your mom's cookbook and you really want to bake a cake, There you are just going to check a set of instructions, exactly follow the same set of instructions without deviating from it. That becomes your sort of, you're following the same set of steps. That is a part of the static analysis that you can think about, because you're statically following the same set of steps. The other case could be the runtime checks. It's like you don't care about what is in the cookbook. You go ahead and start baking your own cake and start figuring out whether it is getting baked correctly or not, which is something what I do. So yeah, and that same thing also applies to my dishes as well, which is what my wife complains. So this is exactly the same state of affairs is with when we think about kernel extensions. So they are not providing both of these things altogether. And this is where we actually proposed something called Kflex. So Kflex is a very interesting system that actually takes the case of merging both of these safety properties or looking at both of these techniques together. And the way it tries to do is that it tries to segregate the safety properties with respect to when the extension is going to be executed. So when the extension is going to be executed, it actually executes at a certain interface. It has to use certain kernel interfaces to actually work with. And this is where and if you look at these interfaces, they are well defined and they're very narrow. They're like very small number of them are there. So we can always rely on static analysis for them to maintain the performance. Meanwhile, when we think about flexibility we define with respect to the behavior of the extension. And this is where we end up using the runtime checks to design this whole system. So to give you a very basic idea, so here is how a very simple stack looks like, or an application when it is running and it is performing some key value store operations. So this is how it actually looks like. So here, the request is actually flowing from all the way from the NIC to the driver. NIC is your network card, to the driver, to the network stack, and then to the memcached. And then the memcached will perform get and set operations, or look up the operations, and then will respond back. With Kflex, what we are able to do is that we are sort of able to remove most of the layers that are involved there to improve the performance. And the reason we can do is because Kflex allows us to run arbitrary code inside the kernel with safety guarantees. So since I'm a systems researcher and I like numbers, and this talk would be incomplete if I don't put the numbers. So just to give you an idea, here what I'm showing you is on the x-axis the get and set operations, varying get and set operations. And on the y-axis we have got this throughput. What you can see is, and we are comparing two systems. One is the memcached, the traditional design, and our system Kflex, which is being used for porting the memcached. What we can see here is that by removing the layers, by removing the decade-old abstractions that have been added for functionality, we can improve the performance by up to 3x and even reduce the latency by up to 9x, P99 latency. So indeed, Kflex can actually provide us this notion of flexibility, safety, as well as performance at the same time. Now, since we have looked at what is the meaning of efficiency, let's try to take a look at another aspect, which is about heterogeneity. So here I'm going to talk about another work, which is about customizable storage stack that was published last year. This work I'm really proud of because it was one of the ways where we could really rethink about storage stack design. So what is a storage stack? Well, for people who don't know about it, you can draw the analogy of having a library with a set of shelves, and the shelf is storing books. And the library forms your storage media, and the shelves and how you're storing is what storage stacks actually do. So they are responsible for storing your data in a particular fashion that could be actually used. So what has happened over the period is that if you think about storage stacks, they have been the very basic building blocks for systems or for storing data as well. And over the period, based on the application requirement, different storage media have been coming out to cater to the increasing demands or varying demands of various applications. However, the storage stack is still following the decade-old design. If a developer or if a user really want to customize it, they cannot tune it to the way they want it. And one of the reasons when you look at it is that the design is completely intertwined with what are the basic components of the operating system, so of the file system or the storage stack interface. So all the state has been already encapsulated and is pre-packaged and is kept, and that's what is being used. So this is a very classic model of a monolithic design. The another analogy that you can draw is from a pre-packaged frozen pizza, which does not allow you to actually modify it the way you want or have something else. So we actually take an inspiration from there only, and we sort of try to decouple the states in such a way that we can have a base layer and a sort of a customizable layer or a core state. So core state is the one that ensures the integrity or the safety and the security of the data that you're actually saving. Meanwhile, the auxiliary state comes for the performance purpose. So you can think about that core state is like a base layer. When you want to make your own pizza, it forms a dough. Meanwhile, the auxiliary state is corresponding to the desired toppings that you want to add on top of it, along with the sauce that you like about. So by taking this kind of an approach, we further come up with a very simple design of a new architecture that was called Trio. So Trio had this very interesting architecture where there were 3 generals. So one of the general was responsible for maintaining the integrity of the core state. The another general was responsible for maintaining whatever changes are being made, whether they are correct or not, and notify another general that is maintaining the core state. And finally, the third general was the one that was exposed and was being maintained by the applications. So the applications had full control of designing their own file system stack the way they wanted it. So here is another performance numbers which I'm going to show is on one of the side I'm showing the Nova or the kernel file system, which is an old file system or a decade old. Now it is a decade old file system, which is difficult to change, difficult to customize, and it's not really flexible. And then there are 2 different file systems that we actually designed, or the storage stacks, that have been customized for the specific needs. So by just customization, we first actually remove the unnecessary overhead that actually comes from the decade-old system design, and which actually gives us around 60% more improvement in comparison to what the old system was giving. Now, since we are talking about customizability, flexibility, and performance, we take a step further and further specialize this design and come up with the different interfaces that can further give us 30% performance improvement. Well, this has not been the only case that my group has been looking at. We have done a lot of work in the area of OS design, to targeting concurrency primitives, to targeting concurrent data structures, designing networking primitives, to even trying to scale network functions as well. So I would say, like, from efficiency and heterogeneity point of view, our group has been quite proactive in terms of looking at different aspects of it. So in summary, what we have been doing is that there is a way of tailoring today's system software for tomorrow's need. But first, we have to understand how existing hardware is actually behaving and understand its limits. The second aspect that becomes very important is that the abstractions or the approaches that we have taken in designing today's systems or the system software that is existing, it is sort of not applicable for tomorrow's need. We have to actually revisit them. And one of the ways that we have actually started looking at is more on the lines of state separation and right set of abstractions that could allow us to customize, make them flexible as much as we want. And by doing this, we can not only support the general purpose applications, but we can also support very specialized applications as well. Now, this talk will not get over unless and until I actually give my regards to the set of people who have actually shaped me. So the first set of people who come to my mind are my advisors who have shaped me during my PhD, Taisoo Kim and Changwoo Min. So Taisoo gave me the full freedom to do whatever I wanted during my PhD, and he also showed me what are my limits when I was working as a PhD student. Meanwhile, Changu was the one who actually showed me the path of trade-offs, what is important, what is not important, and how to even handle your other advisor. The other set of people who are actually shaping me today are Ed, Natasha, George, and Katrina. They have been involved in shaping up my research direction, to my teaching, and other aspects of my life at EPFL. And there's also another person, who is Sudarshan Kannan. He's a faculty at Rutgers. He's a person whom I always reach out to, who has always given me the best advice, be it life or work. Finally, when I talk about, no, second, it's the second last. It cannot be finally. We have a lot of people. Are my team members, Yuji, Vishal, Tao, Pan, Kartikeya, Musa. They have been, for me, the most interesting parts are my meetings, where I actually get to learn new things from these folks all the time. And I would also like to acknowledge DU, who actually graduated, who actually was a postdoc in my group and has joined Peking University as an assistant professor. The lab is incomplete, or the lab cannot really function without the assistants at EPFL, which is what I have learned when I talk to people outside, colleagues outside EPFL. And I am really grateful for Maggie, because she has been always helping me out, whether be it personal stuff or whether be it about how to handle even French at some times, which I'm not very well versed with. Thank you for listening to me.